Bismillahirrahmanirrahim. We start new chapter in operating system, that is processes. In chapter 1, we discussed in detail what is an operating system, and we had different definitions for operating system on the basis of the functions it performs. Then we discussed different objectives or goals of operating system, and also discussed the history of operating system, in which we discussed different types of operating system that have been developed over the years. So that was an introductory chapter on operating system, and from now on we will be discussing different functions that operating system perform. So before proceeding to the functions, the basic functions or the important functions that operating system perform, we need to first discuss the actions it performs on user activities or user tasks. So this is the chapter processes, in which we will be discussing how operating system handle user tasks. Process here means user activity, user task, user program. So let's proceed with the discussion agenda that we are going to discuss in this chapter. So the outline is in front of you. We are going to first explain what is a process. So after understanding the concept of process, we then will move on to discuss different states that a process generally show during its lifetime. And then we will be discussing how a process changes its state, how it moves on from one state to another. So the state transitions will be discussed diagrammatically. Then we'll be discussing the block having process control information. What is it and what sort of information it holds? What are different operations that generally a user can perform on his process or an operating system performs? We'll be discussing different operations. And then at the end, we will be discussing process scheduling, how a process is scheduled in your system. That includes different types of scheduling queues in which your process stays over its life cycle. What are different types of schedulers performing different actions on user process, and then how context is changed from one process to another. So this is the discussion agenda that we are going to discuss in this chapter. So let's proceed. The first topic today that we are going to discuss is to have an understanding with the term process. What is a process and how we can differentiate it with the word job that we had used in chapter 1. So let's proceed with the discussion. If you remember, in chapter 1, we discussed the word job, and what I had told you was that job is any user task. I had also told you that for now you need to have job as a user task, but in the coming chapters I may be going to change the definition for the job. So now is the time to change the definition. Now there are two terms, job and a process. Both refers to user job, or both refers to user task, user program, user application. But there is a slight difference between the two. Job mainly refers to user task that is not currently being executed on CPU. So a job is that type of user program, user task or user application which is in rest condition. It is not being executed on processor. While on the other hand, a process is mainly a program, a user job, a user task, a user application which is in execution. So there is a slight difference between the two. A job, both are user tasks, user applications, user programs, but the job is that type of user application which is not being executed on processor, while a process is a user task, a user application or a user program which is in execution. That means it is being executed on processor. Process actually means something, an ongoing activity. If we define the word process, so it is something that is being happening. So what is being happening, what is being executed is known as a process is in computer terminology. So I think you must have understood the difference between the two terms, job and process. Job and process both refers to user task, user application or user program. Type of user programs which are not being executed currently on CPU, while a process is a user program which is in execution. So a process execution needs to be progressed in sequential fashion. That means your process consists of different instructions and those instructions are executed in sequential fashion, one after another. Similarly, your computer has multiple processes at the same time being stored in RAM. So the processes that are stored in RAM are stored one after another and their execution is also ensured sequentially. That means they are executed on CPU one after another. In the sequence they are stored in RAM, in similar sequence they are being executed on CPU. But one process needs to be executed on CPU at a time. So process execution normally progresses in sequential fashion. Now, user program or a process has three types of information. First is the program counter. Program counter, or simply we can call it or we denote it with PC. PC is actually a register that holds the address of next executable instruction within the program. For example, you commonly use functions in your program. So when a function is called, your program jumps to that specific function wherever it is stored in RAM. So normal sequence of program execution is broken here. Control is transferred. Control of what? The control of processor is transferred to the calling function. And when that function completes its execution, the control comes back to the main function. Now, where in main function the control of CPU has to be returned? So this information is generally stored in this program counter. The address of the instruction on which the control of CPU has to be returned within main program. So this address is stored in program counter. For example, this is your main program, main function, and you have used different functions within main program. So many statements, and then there is a call to function A. And after function A, there are further sequence of statements within main. Now, when your CPU reaches to this function, it is actually a jump to some other location, as function A is not defined in this program. So function A is defined somewhere and stored somewhere else in RAM. So the control is transferred to function A. And when function A completes its execution, the control of processor needs to come back to main. Now where in main? Either start of the main, mid of the main, or end of the main. Generally, the control is transferred to the next executable statement after the calling function. So this was the statement on which the control needs to be transferred back. So the address of this instruction is stored in program counter, which ensures the sequential execution of instructions within a program. So program counter is a register that holds the address of next executable statement within your process. So this is what is the next executable statement after jumps. For example, jumps in case of functions. When the control comes back, where it has to go to the next executable statement. And how it gets the address of next executable statement? It gets it from program counter, from this register. So this register tells operating system where it has to bring control back in main function. So your program has program counter, first thing. The second thing it has is the stack. Stack is a data structure. It's data structure, how data is to be organized in your application or in your process. So stack is a form of data organization. Stack generally represents these executable statements. These statements are generally referred to as stack. And then you have the data section. That data section, the variables, the arrays, the constants that you generally declare in your program. So stacks are the executable statements. Your instructions are organized in shape of stack, while there is some data section that includes the variables, the constants that you declare in your program. So your program consists of these three components: a program counter, which is a register that holds the address of next executable statement. Then it has the stack. Stack is a form of organization of instructions within the program. So your executable statements are organized in shape of stack, and then there is a data section that includes the variables, the constants that you generally declare in your program. These three components collectively form a process. So this is the representation of your process in RAM. Here you can see process size may vary as per your requirement, starts from 0 to any length that you want to give to your process, your application. So stack, as I just said, it is the set of executable statements organized in shape of stack. Then there is a heap. Heap is again a type of data structure. Heap actually represents the collection of non-executable statements that you generally add to your programs. For example, the comments, the white spaces, the formatting characters, they are those statements which are generally non-executable. They do occupy space in your program, but they do not bring any effect on program results. Comments occupy space, but they do not change the results of your program, or they do not have any important role in program execution. They are just for the understanding or for the formatting purposes. So heap are part of those non-executable statements that do increase the size of program, but they have no role in program execution, or they have no impact on program results. And then the data section that I just elaborated, your process contains some data section, sort of variables, constants that you normally declare in your program. And then there is some textual part, if it is a Word document or if some sort of typing software. So the text that you write in your application comes in this section. It may be optional. Every application does not require the textual part, but some applications are for text, such as your word processors, your PowerPoints. So the text part goes here. So this is how your process appears in RAM. These are the components that form your RAM, that form your process within the RAM. So now we have developed our understanding with the word process. Process and job are two similar terms with slight differences. Now we proceed to discuss different states that a process normally show during its lifetime. A process shows different states, such as matter has different states. Matter shows 3 different states: solid, liquid, and gases. Similarly, your task, your job, your application, which is in execution. So during execution, it shows different states. What are those states? Let's discuss that. So these are some of the states. I'll be discussing few more in the coming slides, but the common are these few. Your program or your process, when it executes, it normally changes its states, or it keeps on changing its state during its lifetime. When you click some new application, so a new process is created and started running. So the process, when you click start new, that means you have created some new application. A new application, a new process has been created and started to run on CPU. Now, after creating, when it gets executed on CPU, so from new, the state has been now changed to running. Running means the instruction within the process are now being executed on CPU. So the state has been changed from new to run. After running, there can be some waiting state, or there can be some scenario, some point in your process when process requires response from user. For example, some input statement has been encountered in the running process. So there the process will have to wait for the user to give it some input. So that state, until you give it input to the process, it will not proceed ahead. So it will have to wait for the user to respond. So that state is known as the waiting state, or we can also call it the block state. Here, the process is waiting for some event, such as it requires user to give it some input. So when you give input to the process, it starts executing again, or the instructions are then being executed on the CPU again. So from running, its state is changed to blocked or wait state. Keep in mind, I'll be discussing some more waiting states later on, but this waiting, which is known as the blocked, this is actually an active waiting. We'll be discussing some passive waiting later on. Blocked state, where a process is waiting for some event to happen, is actually an active waiting state. That's why we differentiate it with other type of waiting, which are passive waiting. We'll be discussing them later on, and we call it as blocked. This is an active waiting. Then after waiting, a process then acquires another state which is known as ready. Now when you give input to the process does not automatically goes to the CPU. It now has to move on to the RAM. At the tail of the RAM has the processes which are ready to be executed on CPU. So after having your response, the process goes back to the tail of the RAM. The tail of the RAM, or the structure of RAM, means is in the form of a list. That means the processes that are ready to be executed are stored in RAM. So what is ready state? The process that is waiting to be assigned to processor. So once it has received your input, now it requires to be assigned to processor again to get executed. But since processor is not free at that time, another process has been executed on processor, so this process needs to wait for its turn. And where it has to wait? It has to wait in the ready state. Now again, ready is another waiting state. Those processes which are ready to be executed on processor are waiting in RAM. So this is again an active waiting state. So as soon as the processor is free to be assigned to this process is then assigned to processor, and instruction within this process are started to execute. So now from blocked, you have given the input to the process. From blocked, the state of the process has been changed to ready. Now the process is in RAM, ready to be assigned to processor. After execution, suppose your process has completed its execution, so the state of the process is then changed to terminated. Terminated means the process has completed its execution. Now it does not require to be further stay in your system, so it has to be terminated. Terminated means your process is now to be closed. Now there are two types of termination. One type is normal termination and other is abnormal termination, or we call it abort. This is one type is known as normal termination. In normal termination is generally we term it as terminated, where a process smoothly completes its execution and requires to be terminated. So it is normal termination when you get the results out of your process and process goes to its end. Either you close it or it closes automatically after giving you the results. There is another type of termination which we call it abnormal termination, or we generally call it abort. Here, in some cases, a normal running process may reach to some condition which may not be met at the time. So your process may respond abnormally. If the condition may not be met at the time, or it sometime process responds abnormally. So in that case, a running process which is not functioning properly, or which is requiring some resources which are not currently available, so that application or that process is by force terminated, either by your operating system or you terminate it yourself. So the process which has been terminated in the middle of its execution due to whatever reasons, either it is requiring resources which is not currently available, or it is functioning abnormally, so that application is by force killed. So this termination is known as abnormal termination, or we call it abort. So here you abort a process by yourself, or operating system kills it itself. So these 5 are the common states that your process observe during its lifetime. New process is created, and when it starts executing on CPU, the new state is changed to running. And when it requires some event, some response from user or some response from the system, then there it has to wait for that response, which is known as the blocked state. And after receiving the response, then it has to wait for its turn to be executed again on CPU, and the waiting is generally done in RAM in the shape of ready state. And then after completing its execution, a process goes to termination. Termination can be normal or it can be abnormal. The next point that we are going to discuss, after having an understanding with the term process and discussing different states for a process, now we are going to discuss how a process changes its state, how the transition between the states is being done within a process. So the state transitions along with the diagrams will be discussed next. This is a common two-state transition, a two-state model. The very common states, which is the ready state, what is a ready state? The processes that are ready to be assigned to processor, they are stored in RAM in sequence, one after another. I had given you diagram of RAM in chapter 1, if you remember. It is a sort of a list. Processes are stored in RAM in this way. Top location is occupied by your kernel. If you remember, I had told you the top location is occupied by kernel, while rest of the RAM has been divided among user processes. So they are stored in sequence in this way. Process 1, process 2, process 3, and so on. So little space is occupied by the kernel, while rest of the space is divided among user applications. So this is the shape of your RAM, structure of your RAM in shape of a list. Now, this is actually showing the ready state. All the processes which are stored in RAM are actually in ready state. So whenever processor is available, the first process in the ready list will be assigned to CPU. So when a process is selected, for example, this is the first process P1. P1 is at the top of RAM. It is assigned to CPU. It has been assigned to CPU, so its state changes from ready to run. Now it has been executed on CPU. The instructions within this program, within this process, is started to be executed. Now this is the event which happens to change the state from ready to running. Keep in mind, Dispatching function, this is an event or this is a function of operating system which changes the state of a process from ready state to running state. Keep in mind, this dispatching function is only used when a process changes its state from ready to run. You are not allowed or you are not supposed to use this function between other states or even the reverse of running to ready. So dispatching activity is only performed between ready and run when a process which is in ready state has to be assigned to CPU and its state is changed to running. So here means dispatch function has been called. Dispatch means to send something. Now what is being sent? A process in the ready state has been sent to CPU for running state. So this dispatching function is only used between ready and run, not even in the reverse order. Keep in mind. So when the process is executing on CPU, that means now its state has been changed to run. And after running, it may happen that the time it has been assigned to run on CPU gets expired. We will be discussing how time runout happens in coming chapter. Since you have a single processor and so many processes, these are so many processes which are required to be executed on single processor. So generally time sharing means CPU time has been shared among these different processes stored in RAM. So if a running process reaches its time limit, the time that it has been assigned to run on CPU, when that time limit has been reached, so operating system takes a CPU by force from that running process and sends the process back to the ready state. That means it is sent back to the RAM. And why it is sent? Because the timeout happens. The activity which returns a running process to ready state is because the time that of CPU that has been assigned to this process gets expired. So running process is by force stopped in the middle and it is sent to the ready state. But keep in mind, before sending it to ready state, its program counter has been updated. Program counter means when next time this process will come, it will not start from the start, it will not start execution from the start of the program, rather from the point where it has been stopped in the middle before sending it back to ready state. It will start execution from that point. So the address of that location is stored in the program counter and then the process is sent back to the ready state. So when next time P1 will come back again, it will start executing from the address it will get from the program counter. So from that address it will start executing again. If again it reaches time limit, so then again program counter will be updated on the statement. It is going to be stopped again and will be sent back to the RAM. So this is a two-state model, a very common model. When a process in ready state is dispatched to CPU and the state changes to running, as it is the instruction within the process are getting executed on CPU. And when the CPU time that has been allocated to this process gets expired, so that process is then by force stopped by operating system due to time run out and is sent back to the ready queue. Now where in ready queue? It is not supposed to acquire the first location again. First location has been occupied by another process. As you know, the process gets shuffled. So it has to come to the tail of the ready queue. It has to stay here. So after time run out, the process has to come at the tail of the RAM, at the tail of the ready queue, as next process now P2 will go to running state. So the process execution happens or process executes in sequential fashion, as the first statement I mentioned in the first slide. Now this process 1 has to wait in RAM until it's turn to go to the CPU. Till then it has to wait in RAM. It is ready to be executed, but since CPU is not available, so it has to stay in RAM until the CPU is available next. So this is a two-state model, a very common model. Ready state has been changed to running state. Why? Because a function has been dispatched, a process has been dispatched to CPU, and when the CPU time limit has reached, the process from the running state is sent back to the ready state. I hope this two-state model is clear to you. That is all for now. We'll continue our discussion on process state transition and we'll discuss further more states. We have discussed two-state model and we'll be discussing some more states in the coming lecture. In today's discussion, we started the chapter processes and developed our understanding with the term process. A process is a user task in execution. So a process is user application which is being executed on CPU. Then we discussed different states which a process holds during its lifetime. 5 different states have been discussed and I'll be discussing 2 more states in the coming slides. 5 states are the new state when a new process is created, then the running state when the instructions within the process are getting executed on processor, so it is the running state, and then we discuss the blocked state when a process comes to stop or comes to halt for some event to happen. So the process waits for this event to happen before it continues its execution. So that state is known as the blocked state. Generally, for input, it requires user to give it some input. So there it stops its execution. That doesn't mean it has completed the execution. It has stopped for some event to occur, or the user gets input or user gives it some input before it continues its execution. So the blocked state is the active waiting state, and then after block, when you give the input to user program, the state of the process then becomes ready. From running it goes, from blocked it goes to running, it goes to ready. That means now the process requires CPU again to get executed. After you give it the input, the event has been completed, so it requires CPU to be executed again. But since CPU is not available at the time as some other process is being executed on it, so that process has to wait for its turn in RAM. So the RAM is a collection of ready processes, those processes which are ready to be executed. So from block, the process changes its state to ready. And then the termination state, when process completes its execution, it generates the results, gives output, and wants to get terminated. So the termination is the ending state of a process. When you close the application, that means the results have been generated, the output has been given to you. Now you do not need the process anymore, so you close it. That is the termination state. But termination, there are 2 types of termination. The normal termination, in which the results are generated and process does not require anymore to be in your system, so it has to be closed. That is normal termination. But there is another type of termination which is abort or abnormal termination, in which a process generally functions abnormally, or it requires resources which are not currently available, so it may hamper the execution of some other processes. So in that case, we by force kill that process during its execution because it may be harmful to some other processes. So that process is by force either killed by the user or killed by the operating system. So that sort of termination is known as abnormal termination, or that we can call it abort. And then we discussed the state transition, and a common two-state model has been discussed in detail. We will continue the state transitions in the coming chapter as well. If you have any confusion, any queries, you can email me your questions. That is all for now. I thank you all.